This conference will now be recorded.
Yeah. So dear students, in the last session, we have discussed about sum of two random variables and sum of n random variables and the density function and distribution function of sum of two random variables and sum of n random variables. And also we have seen central limit theorem, right? And we have started the operations on multiple random variables. So in the last class, I said that the operation that we can apply on the function of random variables is expectation. So we have seen what is the expectation of the function of random variables. If I take the function of random variables of g of x comma y, the function of random variables as g of x comma y, we have seen the definition for e of g of x comma y, expectation of g of x comma y. So now I am going to see the statistical behavior of the random variable which is derived by adding two or more random variables. That is, to know the statistical behavior, I am going to apply the operation on that particular random variable. And the only operation is the expectation. I am going to see now expected value of the function of random variables. Right? So here, the expectation of function of random variables. The same concept can be extended even to n number of random variables later. That is, so here expectation or expected value of sum of random variables. So if x bar, y bar and z bar are the means of x, y and z respectively, then how can I write that z bar? Z bar equal to e of z equal to e of g of x comma y, or we can write it as expectation of x plus y. General representation of expectation of sum of two random variables, that is e of x plus y, equal to what? Integral minus infinity to plus infinity, integral minus infinity to plus infinity, x plus y into fx comma y of x comma y dx dy. It is a joint density function of two random variables x and y, right? Therefore z bar equal to, how can I write this? I am separating into two integrations. One is x into fx comma y of x comma y into fx comma y of x comma y, right? So here I'm just rearranging the terms, and I am taking here one integral for y and I am taking one integral for x. We all know that this particular integration is nothing but marginal density function, that is fy of y, right? Similarly here it is the marginal density function of fx, that is for x, that is fx of x. So ultimately we can write here the resultant integration becomes expectation of x. Why? Because it is nothing but integral minus infinity to plus infinity x into fx of x dx. Similarly here integral minus infinity to plus infinity y into fy of y dy. So it is nothing but expectation of y, and therefore it is x bar plus y bar, right? Right. So it is nothing but the mean value of the sum of two random variables. Similarly here, I can take the variance, and we know the formula for variance. Variance is sigma z square equal to sigma x plus y square, right? Or we know the definition for variance, that is expectation of z minus z bar whole square. It is expectation of x plus y or x plus y bar, right? So it is expectation of x plus y or x plus y bar whole square, right? So if I expand this, I can rearrange the terms like this. Since e of x plus y, in the sense e of x plus e of y, e of x is nothing but x bar, e of y is nothing but y bar. So I can rearrange the terms like this: x minus x bar plus y minus y bar whole square. If I expand the terms, I'm going to get this, that is a minus b whole square, a plus b whole square formula, a square plus b square plus 2ab, right? Similarly here, it is nothing but sigma x square, it is nothing but sigma y square, it is nothing but, if I take the expectation into this, it becomes x2 into expectation of x into x bar into y bar, and like that here the corresponding values can be multiplied and the resultant can be represented like this, right? Direct step I am writing sigma x square plus sigma y square plus 2 into expectation of xy minus, here if I take the expectation here, it becomes x bar is constant, therefore x bar into expectation of y, expectation of y is y bar, x bar y bar minus y bar is constant, again expectation of x is x bar into y bar, anyway x bar y bar is constant, expectation of constant is again the same constant x bar y bar, and this minus x bar y bar and plus x bar y bar will get cancelled, and the resultant will be sigma x square plus sigma y square plus 2 into expectation of xy minus x bar y bar, that is sum of two random variables, variance of sum of two random variables, right? Now we have seen what is the statistical mean of the sum of two random variables by applying the operation, that is expectation. We have seen what is the statistical variance of the sum of two random variables, sum of two random variables by applying the operation, that is expectation, right? So finally what we have concluded, that expectation is used for finding the statistical parameters, right? So similarly here, anyway, we have discussed about the statistical parameters by applying the operations for a single random variable case. And there we have derived the moments. We have taken the moments. From the moments, we have derived the statistical parameters. Similarly here, we are going to derive the moments to find the statistical parameters of multiple random variables. So where we use joint moments, and in the single random variable case we simply call moments. Now it is multiple random variable case, therefore we call joint moments. So the joint moments can be taken again two ways. One is joint moments about the origin, joint moments about the mean, that is central moment, joint central moments. First case is joint moments about the origin. We can define like this. For the two random variables x and y, the joint moment about the origin is denoted by m suffix nk, and is denoted by m suffix nk equal to expectation of x power n into y power k, or equal to integral minus infinity to plus infinity x power n into y power k into fx comma y of x comma y dx dy, right? The single random variable case only we used to have m suffix n equal to expectation of x power n. Now we got expectation of x power n into y power k, right? Where fx comma y of x comma y is the joint density function of two random variables x and y, right? Simple formula. And here if I take k equal to 0 or n equal to 0, in both the cases I'm going to take the function as either x power n, expectation of x power n, or expectation of y power k. If you observe these two, ultimately here you can get some idea, that is this function is nothing but the moment about the origin, moments about the origin in the single random variable case, right? Single random variable case. And therefore here the sum n plus k is called the order of the moments, in the sense here m02, m20 or m11 are all the second order moments of x and y, and m01 and m10 are first order moments, right? Why? Because n plus k represent the order of the moments, right? Here if n equal to 0, k equal to 0, what is going to happen to the function here? Ultimately it is equal to 1, that is the zero order moment is always 1. Zero order joint moment about the origin is 1. And if n equal to 0 and k equal to 1, m01 it becomes expectation of y, that is y bar. It gives the mean value of the random variable y, m01. M10 will give the mean value of the random variable x. It is one of the statistical parameter. This y bar is statistical parameter mean, and x bar is statistical parameter, that is statistical mean of x. In the sense, the first order moments are giving the mean values of the random variables. Similarly here, if I take n equal to 0 and k equal to 2, it is giving what? The mean square value of the random variable y. And m to 0, the mean square value of the random variable x. Again, the statistical parameters. The second order moments m02 and m20 are also giving the statistical parameters, that is mean square values. And if n equal to 1 and k equal to 1, another second order moment, that is m11, is equal to expectation of xy, and it has the great importance in the communications, that is expectation of xy, and will also be called as correlation. That what we'll see later. The first order moments m10 and m01 are the expected values of the random variables x and y respectively, just now we have seen, and are the coordinates of center of gravity of the function, joint density function fx comma y of x comma y. So m10, m01 are also called the coordinates of center of gravity. Very, very important point, right? So in the competitive exams, so m10 and m01 are called coordinates of the center of gravity, right? And the second order moment m11 indicates an important quantity, as I said, the correlation between the two random variables x and y, and is denoted by rxy. So what is that m11? M11 is nothing but correlation between the two random variables, and we'll denote it with rxy. Rxy is nothing but the correlation between x and y, or expectation of xy, right? Therefore, we can write like this: rxy equal to m11 equal to expectation of xy equal to integral minus infinity to plus infinity, integral minus infinity to plus infinity, xy into fxy of x comma y dx dy, right? That if the two random variables x and y are statistically independent, then the correlation can be written as, if they are statistically independent, we all know that what is the condition for the statistical independent? One is the joint density function equal to product of individual density functions. With respect to expectation, E of xy equal to what? E of x into E of y. Yeah, that is, the joint density function becomes fxy of x comma y becomes fx of x into fy of y. So therefore it is E of x into E of y, right? Next, the above expression stands as the sufficient condition to check whether the random variables are correlated or not. So we can check whether the random variables are correlated or not. Also, if the rxy equal to 0, the two random variables x and y are said to be orthogonal to each other. Orthogonal to each other. If rxy equal to 0, if expectation value equal to 0, you can call it as the two random variables as orthogonal to each other. xy are orthogonal. There is no similarity between the two random variables. That is, if rxy equal to 0, we call it as orthogonal random variables. Very, very important point, right? For the case of n random variables, how can I find out the moments, joint moment about the origin? If I take the random variables from x1 to xn, then the n1 plus n2 plus n2, n3 up to nth order moment can be represented like this: expectation of x1 power n1, x2 power n2, and up to xn power nn. Understood? Right? Right. Where n1 to nn are integer values. Right? Fine. Now let us come to the joint central moments, or moments about the mean, like this. Here, for the two random variables x and y, the joint central moments are the joint moments about the mean are denoted by mu suffix nk, and are given by mu suffix nk equal to expectation of x minus x bar whole power n into y minus y bar whole power k, right? Whole power k. So similar to the single random variable case, and there we used to take mu suffix n equal to expectation of x minus x bar whole power n. Now another term is added here, y minus y bar whole power k. How do you write in the integration form? Integral minus infinity, double integral minus infinity to plus infinity, x minus x bar whole power n into y minus y bar whole power k, fx comma y of x comma y dx dy. So usually the moments are meant for finding the statistical parameters. And just now we have seen how to find the statistical parameters by using the joint moments about the origin. We're able to derive the statistical means of the random variables by finding the first order moments, and we're able to find the mean square values of the random variables by finding the second order moments. We are able to find the correlation value by taking the second order moment m11, and we are able to check whether the two random variables are orthogonal or not by checking the condition, that is the correlation factor equal to 0 or not. And now we are coming with the joint central moments to find the statistical parameters. Let us see how to find, right? Here, if n equal to 0 and k equal to 0, again the 0th order moment becomes 1. If the first order central moment, that is n equal to 0 and k equal to 1, the first order central moment is absolutely equal to 0. That may be mu01 or mu10, both are zeros. If I take the second order moment, that is n equal to 0 and k equal to 2, it is giving what? The variance of the random variable y. Similarly, if n equal to 2 and k equal to 0, it is giving the variance of the random variable x, that is sigma x square. Similarly here, if I take the second order central moment, if n equal to 1 and k equal to 1, the mu11 becomes expectation of x minus x bar into y minus y bar, which is equal to expectation of x minus x bar into y minus y bar, right? Simple. So here the second order moments mu20 and mu02 are just the variances of the random variables x and y respectively. That is, mu20 and mu02 are giving the statistical parameters that are those parameters are nothing but variances of x and y, right? And the second order moment mu11 is a very important quantity. It indicates the covariance of the random variables x and y, and denoted by the symbol COV of x comma y or CXY. A new term is here, that is covariance. Covariance of x comma y is denoted by COV of x comma y or CXY. And we can write the definition like this: CXY equal to mu11 or which is equal to expectation of x minus x bar into y minus y bar, or CXY equal to expectation of, if I expand the term, xy minus xy bar minus x bar y plus x bar y bar, and the resultant can be taken like this: CXY equal to RXY minus x bar y bar, or RXY minus expectation of x into expectation of y, right? So what is RXY? Nothing but E of XY, or correlation. The relation between covariance and correlation is what? CXY equal to RXY minus E of x into E of y. And here, x and if at all if x and y are independent or uncorrelated, just remember, uncorrelated or independent, then Rxy equal to E of x into E of y. Be cautious. That is, if Rxy equal to E of x into E of y, we call the random variables as independent or uncorrelated. If at all if Rxy equal to 0, we call it as the random variables as orthogonal random variables, right? Then we can write the covariance as equal to 0 if they are independent. If the random variables are independent, the covariance is equal to 0, right? And if at all, if x and y are orthogonal random variables in the sense we know that rxy equal to 0, then what is going to happen to the covariance? Covariance equal to minus x bar y bar, or minus e of x into e of y, right? These are the conditions, different conditions. And now, what is the condition for the orthogonal random variables? The two random variables are said to be orthogonal if at all if the correlation function rxy equal to e of xy equal to 0. When the two random variables are said to be independent, if at all if the correlation function rxy equal to e of xy equal to e of x into e of y. So whenever the two random variables are independent or uncorrelated, what is going to happen to the covariance? The covariance will be absolutely equal to 0. If at all if the two random variables are orthogonal, what is going to happen to the covariance? The covariance equal to minus of means of random variables, that is x bar into y bar. Am I clear? Right. That is cxy equal to 0 if either x or y has 0 mean value. Of course, if there are 0 mean values, cxy will be equal to 0, right? And the other one is other new parameter we are going to introduce here, correlation coefficient. The normalized second order moment. Normalized second order moment. Second order moment is what? Mu11. The normalized second order moment is known as the correlation coefficient of x and y. So how do you represent this? Mu11 by under root mu20 into mu02. We represent the correlation coefficient with rho or rho suffix x comma y. Rho or rho suffix x comma y. Or we can also represent like this, covariance cxy by sigma x into sigma y. Right? Sigma x into sigma y. That is normalized second order moment or correlation coefficient of x and y. Thus, we can write rho as expectation of x minus x bar into y minus y bar by sigma x sigma y, and sometimes we can also write it as expectation of x minus x bar by sigma x into x by y minus y bar by sigma y, right? That is rearrangement of terms. This is all about correlation coefficient, and its value always lies between -1 and +1. The correlation coefficient value range is from -1 to +1, right? For n random variables, the joint central moment is given by, here we can write the joint central moment for n random variables, right? Expectation of x1 minus x1 bar whole power n1, x2 minus x2 bar whole power n2, and up to xn minus xn bar whole power n suffix n. Fine. And we have seen what is covariance. Let us see some properties of covariance. So the covariance is always symmetric, in the sense if you find the covariance of x and y or y and x, both are same. Cxy or cyx, or COV of x comma y or COV of y comma x, both are same, symmetric. And the other property is constant will not vary. That is, always covariance of x comma c is nothing but, sorry, it is covariance of x comma c is equal to 0, right? So here a small change here, it is not it is 0. Covariance of x comma c is 0, right? So now covariance of x comma x, if I find the covariance of the random variable with itself, that is covariance of x comma x becomes the variance value, that is variance of x comma x. Here also it is variance of x, I can say. So I cannot say variance of x y comma x, that is x comma x. So I repeat here, the first property is covariance of x comma y is covariance of y comma x, that is covariance is symmetric. Second one is constant don't vary, that is covariance of x comma c is 0, and covariance of x comma x becomes variance of x, and covariance of x plus y comma z becomes summation of covariance of x comma z and covariance of y comma z. It is called addition rule. Addition rule, right? And covariance of c into x, that is multiplied by a constant comma y, becomes constant into covariance of x comma y, where c is a constant. So these are all the properties. Covariance of a plus b into x comma y, so that is it becomes, if at all if a and b are constants, it becomes b into covariance of x comma y. That is simple change. Now a bilinearity property, very important property. If I find the covariance of ax and by, it becomes ab into covariance of x comma y. Or I can also take in this way, if at all if I take covariance of ax plus by comma cz, it becomes ac into covariance of xz comma bc into covariance of yz. These are all some basic properties of covariance. You can prove them. You can prove them by taking the general definition of covariance, right? So no need to worry about the proof. You can just simply prove by taking the general formula of covariance. Covariance, that is covariance of x comma y equal to expectation of x minus x bar into y minus y bar, right? So these are 8 properties. The first one is about symmetric. Second one is the constant value don't vary with the covariance, and the third one is the covariance of the random variable x itself equal to variance, and the fourth one is addition rule, and the fifth one is if at all of the random variable is multiplied by the constant, and the covariance will become constant into covariance, right? And similarly here we have discussed about bilinearity properties, right? So these are the properties of covariance, some of the properties of covariance, right? So now let us take a simple problem. For the random variables x, y, z, if z equal to ax plus by, where a comma b are constants, determine the variance of z in terms of sigma x, sigma y, and rho xy. So very important. We can also consider this as a property, and sometimes you can expect in the form of a problem. So what is the given question here? Z is defined as ax plus by, and now you're asking to show that the variance of z, that is sigma z square, as equal to or in terms of sigma x, sigma y, and rho xy. What is rho xy? Correlation coefficient. What is sigma x? Standard deviation of x. Sigma y, standard deviation of y, or square root of variance, right? So here simple solution, we all know that z bar equal to expectation of z are equal to e of ax plus by, or I can write it as ax bar plus by bar. Simple, right? Now we are supposed to find the variance. So variance equal to what? E of z minus z bar whole square. I'm substituting the z here, z and z bar. So what is z here? Z is nothing but ax plus by. Z bar is nothing but ax bar plus by bar. And after rearranging the terms, I'm able to write the expression like this. Direct step I have taken, right? Now, if I expand this by using a plus b whole square formula, I'm going to get the expression like this. A square into expectation of x minus x bar whole square plus 2ab into expectation of x minus x bar into y minus y bar plus b square into expectation of y minus y bar whole square, right? So now it is nothing but e of x minus x bar whole square is sigma x square, e of y minus y bar whole square is sigma y square, and in between we have expectation of x minus x bar into y minus y bar. In fact, it is nothing but the formula for covariance. or the covariance can also be written in terms of correlation coefficient and sigma x and sigma y like this, right? So therefore we are able to define the variance of z in terms of sigma x, sigma y and rho xy. Understood? And the simple problem. Now the next topic is conditional moments. So how to write the conditional moments? So if at all, if x and y are any two random variables with the joint probability function. So we have defined a conditional probability. We have defined conditional density. Now we are now moving to conditional moments. So if at all, if any random variable is giving, I mean random variable on particular random variable, we are giving some condition using any other random variable or using any event from the other random variable, and how to find the statistical behavior. That is, by finding the moments, you can know the statistical parameters, right? So therefore here, if at all, if x and y are random variables with a joint density function f of x comma y and the marginal functions fx of x and fy of y, the conditional density function or conditional probability density function of y, given that x equal to x, is defined as h of y given x equal to f of x comma y by fx of x. We know that. We have derived this conditional density function h of y given x equal to f of x comma y by fx of x, right? Right. So now let us take discrete and continuous case, conditional moments for discrete case, and next we are going to see for continuous case. If at all, if the random variable is discrete, the conditional mean moment in the sense ultimately to find the statistical parameters, mean and variance. Basically conditional mean of y is, what is the condition here? Given that x equal to x is defined as mu y given x or expectation of y given x equal to summation y into h of y given x, where h of y given x is conditional density function, right? Conditional variance, how do you define? Conditional variance of y given x equal to x is expectation of y minus expectation of y given x whole square given x, or in the short form I can write like this: y minus expectation of y given x whole square into density function h of y given x, right? Or in the simple way, h sigma y given x equal to variance, right? Continuous case, how do you write? Continuous case, instead of summation we take integration, right? Integral minus infinity to plus infinity y into h of y given x dy, right? Similarly variance also in the integration form, right? And here using the same logic we will come with the conditional probability density function and conditional mean value and conditional variance of x given y. We have taken y given x. Similarly, we can take x given y. So let us take a simple problem you can understand better. Now, if the joint probability density function is given by f of x comma y equal to x square plus 3y by 60, where x is equal to 1 2 3 4, y equal to 1 2. Since it is discrete random variable, I am considering the case discrete random variable. Find expectation of x given y equal to 1, or expectation of y given x equal to 3, and also find the variance of x given y equal to 1. Fine. So how to solve? First, I need conditional mean and variance. To find the conditional mean and variance, I need to find what? Conditional density function. To find the conditional density function, first I need to find marginal density functions, right? Prerequisites for conditional mean and variance, I need to know conditional density function. For knowing the conditional density function, I need to know marginal density function. Fine. So first we need to find marginal density function. From the joint density function, the marginal density functions are, how do you write? How do you write the marginal density function? X is having the values 1, 2, 3, 4. Y is having the values 1 and 2. Therefore, marginal density function of x equal to x square plus, that is, so it is the given function, x square plus 3y by 60, that is x square plus 3y by 60 when y equal to 1, plus x square plus 3y by 60 when y equal to 2, and these two values must be added. So therefore fx of x is 2x square plus 9. I'm substituting the y value here, 3, right, by 60. 3 into 1, 3. 3 into 2, 6. Therefore 6 plus 3, 9. 2x square plus 9 by 60. That is fx of x. Similarly, fy of y. How do you find fy of y? Since x is having the values 1, 2, 3, 4. Therefore, to find the marginal function, I need to eliminate x. To eliminate the x, I am substituting the values of x. That is x equal to 1 plus the function at x equal to 2 plus the function at x equal to 3 plus the function at x equal to 4. Therefore, I can get the resultant density function as fy of y equal to 12y plus 30 by 60, right? So by adding all the values, x equal to 1, 1 square, x equal to 2, 2 square, x equal to 3, 3 square, x equal to 4, 4 square. Therefore, 1 square plus 2 square plus 3 square plus 4 square, that is 30, right? Marginal density function. We got marginal density function. What is the next step? Yes. After the marginal density functions, we can also find conditional density functions. And we know the formula for conditional density function. In fact, we have derived it. Fy of y given x equal to fx comma y of x comma y by fx of x, right? So if I substitute here, the density function equal to what? G of x given y equal to x square plus 3y by 12y plus 30. We know joint density and we know marginal density. By substituting them, I'm going to get directly x square plus 3y by 12y plus 30. Similarly, reverse order. I can also get y given x. I'm assuming the function as h. H of y given x equal to x square plus 3y by 2x square plus 9. Now I got from the marginal functions, I got conditional density functions. But what is my target? To find expectation, mean value, expectation of x given y equal to 1. We know the formula. What is the formula? Yes, summation. That is expectation of the function g of x given y equal to 1. The conditional density function, right? Summation x equal to 1 to 4. X into g of x given y equal to 1. Expectation formula, right? So if I simplify this or substitute the values, what is g of x given y equal to 1? G of x given y equal to 1. Substitute y equal to 1 here. X square plus 3 into 1 by 12 into 1 plus 30. Right? If I expand the summation, I'm going to get the value like this. The resultant is 65 by 21. And the next one is finding the expectation of x given y equal to 3. Same process. So, but here what is the formula? Expectation of h of y given x equal to 3. So now we need to substitute x equal to 3 in the function h of y given x, right? If I substitute it, I'm going to get 3 square plus 3y by 2 into 3 square plus 9. If I expand the summation, I'm going to get this value, and the value is 14 by 9. Now finding the variance. What is the formula for variance? We know the formula for variance for discrete random variable. Expectation of x minus expectation of x given y equal to 1 whole square given y equal to 1. We have seen the formula. variance formula, right? So I'm substituting here. So in the place of expectation of x given y equal to 1 whole square into the conditional density function, that is g of x given y equal to 1, by substituting the value x minus, what is this expectation of x given y equal to 1? Just now we have derived in the previous one. In the previous one, first problem, 65 by 21, we got the answer, right? I'm substituting direct value here. X minus 65 by 21 whole square into, it is nothing but g of x given y equal to 1. G of x given y equal to 1. Now, by simplifying this, by substituting the values and by expanding the summation and substituting the values, I'm going to get the answer equal to 0.9909, almost 1. 0.9909. Understood? So first, to find the conditional density, for conditional mean and variance, we need to find the conditional density. To find the conditional density, we need to find the marginal densities. Am I clear? So let us take one problem. If the joint probability density function is given by fx comma y of f of x comma y equal to 4 by 3 into 1 minus xy, the limits for x are 0 to 1, y are 0 to 1. Both are continuous random variables only. And you are supposed to find expectation of x given y equal to 1. Same method, but the only thing is, in the previous problem, we have taken discrete random variables. So therefore, we have taken the expectation in the form of summations. Now it is continuous random variable. So you need to take the sum, you need to take the expectation in the form of integrations. Am I clear? Right? Pause the video and try to solve. Yeah. Coming to the solution. Here, conditional density function. How do you write the conditional density? G of x given y equal to f of x comma y by fy of y, right? So we can find the conditional density. F of x comma y is given function, and you know how to find fy of y. You need to eliminate x. So therefore, integral 0 to 1 4 by 3 into 1 minus xy into dx, right? Formula for marginal density function, right? Condition for marginal density function. Here I'm just finding the integration and substituting the limits. Finally, I got the conditional density function as 4 by 3 into 1 minus xy by 4 by 3 into 1 minus y by 2. And 4 by 3 gets cancelled, and the resultant will be 1 minus xy by 1 minus y by 2. Right? So now let us find the mean value. Mean is direct formula. Expectation of x given y equal to integral 0 to 1 x into g of x given y dx. Substituting the density function. Finally, I got the resultant value like equal to how much? 1 by 1 minus y by 2 into 1 by 2 minus y by 3. Right? So this is the way to solve the problems. So in this session, we have discussed about joint moments, about the origin and joint central moments, and by using the joint moments and joint central moments, how to find the statistical parameters like mean and variance of the random variables. And we have come up with a new parameter, statistical parameter, that is covariance. And what is covariance? What are the properties of covariance are discussed. And also we have discussed the conditional moments, where we have seen the conditional mean and conditional variance, right? So in the next session, we are going to discuss about the joint characteristic function. So which are nothing but the functions which can generate the moments, right? Thank you.